How are you guys? How's it going? Uh, I'm just preparing this sort of somewhat short video on the a brief history of computing because I've been preparing these notes myself, and I feel like they'll be of use to more people if I sort of share them and go over them. They say the best way to study something is to teach, so this is me studying effectively while also trying to help Yi out as well. So this is effectively just a trial run of this. I'm going to be going over the history of computing. I've prepared slides on this. It's all based on the textbook. If you have your textbook, you can follow along. This is all done in one take as well. There's no there's no editing going on here. So I suppose we'll start by defining what a computer is. So what is a computer? So we can start by going all the way back to 1901, the Antikythera Mechanism. This was discovered in Greece off the coast of the Greek island of Antikythera. And it's been considered throughout the last 100 years to be the world's first computer because it was analysed, and they found out that it was used to calculate the positions of planets at different times. So an astronomer could input a time of day or year or whatever, and they'd be able to find out where the planets would be relative to Earth, and they would be able to spot them in the night sky. But in 2020, scientists came to the consensus that this wasn't a computer, but it was a calculating machine. So how is that not a computer? So we can define a computer as a device that we can program to carry out general purpose mathematical and or logical computations. So because we can't program, or because the Antikythera mechanism could not be programmed, we can't call it a computer. It had one single purpose. So we can add to our definition of a computer that we can program it or reprogram it to improve the solutions to a problem, to adapt to different changes in the problem, or to program it for a different problem altogether, which we can't say about the Antikythera mechanism. So a computer is very much a general purpose machine. It can carry out a wide range of tasks instead of just following specific instructions with a specific goal. An example of something that wouldn't be general purpose is a calculator, because it can only carry out a limited number of calculations. You can only do, your addition, subtraction, multiplication, division, your square roots, your whatever. You can do all that on a programmable computer, plus much more. You can't program your computer, your calculator, and bring it into the exam hall for the maths and bring up your proofs or whatever, because that would be cheating. So they're not programmable. So we have a digital computer, the concept of a digital computer, right? So signals transmit data from place to place. You know how a signal works. It can travel through a wire. It can travel audio information, or it can travel wirelessly like Wi-Fi or Bluetooth. So we have two types of signals. We have a digital signal, which is your ones and zeros, so your binary. We would have gone over binary already. Your light switch is binary in a sense that it can be on or off. Then you have an analog signal, which is a variable. The value changes continuously with time, like a volume dial on a radio. You don't have like a volume switch that's either on or off. You can turn the dial and choose how loud you want it to be. It's a variable input. You can check page 119 in the textbook. They give graphs of a digital signal and an analog one. So then we have the concept of an electronic computer. So all these concepts are going to come together. So this would operate through electricity flowing through a material, electrons flowing through a material. They're made using a unique type of material called a semiconductor, usually silicon. Which is interesting in that it has the properties of a conductor and an insulator, so it can be used as a conductor or an insulator, or even both. So it's it can be used to control the flow of electrons, which is very, very important for computing, and it's how almost all modern computers operate. So now we sort of understand the different aspects to a computer. We understand that the concepts, the definitions of it. We can go into the history of it. So let's start back a long, long time ago, right? A pile of stones could be used as a means of keeping track of numbers and storing data. You know, if you had a neighbour that owed you 5 apples, you could take 5 stones, put them in a pile somewhere, and then you could, if you were like, how many apples does my neighbour owe me? You can just check the pile of stones. You're like, oh, there's 5 stones here. They owe me 5 apples. So it's a way of storing data. Obviously, we don't do that anymore. It was replaced eventually by the abacus, which you might have used in primary school. Like, you know, you could do more complex calculations on an abacus than you could with a pile of stones. But still not a computer, because you can't program it. It's got a specific purpose, not general purpose. Fun fact: a computer used to be a person. It was a job, someone who carried out these calculations, such as calculating logs. You know, nowadays you can use your calculator to find out logs, but you know, people would actually have to sit down and calculate logs themselves, which is where the term log tables actually comes from, because the booklet used to be a booklet of these tables that you see here, although this is a much older table, but you know, tables of logs, because you couldn't use a calculator to find them. Then you have, I suppose, the advent of the slide rule. This was invented in the 1600s, and it could be used to calculate the likes of, you know, to calculate these logs and trigonometric functions, square roots and stuff like that. These were used right the way up until the 1970s, when they were eventually replaced by electronic calculators, which of course we still use today. Slide rules, still not a computer. Why? Because we can't program it. It's a specific purpose. You're beginning to see the theme. You know, we can't really call these the first computer yet. The difference engine, this one's quite important. This was invented by Charles Babbage in 1822. It was a calculator designed for solving polynomial equations like quadratics and cubics, like we would do all the time in maths. It had a lot of moving parts. You can see how big it was. It's the size of a car, and it's still not a computer because it has a specific purpose. It's not general purpose. You know, you'll be tired of hearing me say this, but this one is different. Okay, this is another creation of Babbage's. You can see I don't have a picture of it because it wasn't actually made. This is the Analytical Engine. It was designed to carry out calculations and computations on data that was stored on hole punched cards. So literally thick pieces of card with holes punched into them. And you could also write programs and store them on hole punch cards as well to determine the calculations to be carried out on the data. So while this was only theoretical, it was only drawn up, it was never actually built, it is a computer. It matches our definition. It's general purpose. It's programmable. You know, you can write a program, you can feed it data and get an output, and you can reprogram it to do anything you want. So we could arguably call this the world's first computer. Then you have Ada Lovelace. Okay, she is regarded as the world's first computer programmer in history because she actually wrote programs for the Analytical Engine, even though it was never built. So she wrote the first algorithm designed to be run by using machines. So this is a huge moment in computing history, you know, to be the first programmer, even if the first computer was never actually built in the first place. But it's still a milestone. It's still very monumental in computing history. Then we have Alan Turing. Everyone's heard of him. He came up with the idea of the Turing machine. Okay, and this is a very important concept in computing, especially on the Leaving Cert course. There's 4 components to it. So you have a tape with symbols that can be written to and read from. You have a tape head that does the reading and writing, so a head that reads and writes to the tape. You have a state register that stores the state of the machine at any point in time, and then a table of instructions that tells the machine what it should do next, depending on the current state and the symbol being read at that point in time. So this is the basis, the concept of a modern computer. When you think about it, you can, while we don't, you know, use a tape, this is effectively what a modern computer is. You know, scientists could study computers before they were even modern computers, before they were even built, because they had the concept of the Turing machine to study, which is really interesting. Then we move towards electromechanical computers. So these sort of had a prevalence in the 1940s. They used electric switches to move mechanical parts, hence the name electromechanical. An example of this you can see here, the Z3 computer was built in Germany in 1941. This was the world's first digital programmable computer. So remember earlier on we were talking about a digital computer using ones and zeros. So yes, this is the world's first digital programmable computer because it used binary signals. Back to Turing. So we're in the height of the war now. He was part of the team at Bletchley Park who helped crack the German Enigma code, which was used by the Enigma machines. You can see I've got a picture here. These were used by the Germans to transfer messages, and by cracking the code they were able to intercept German messages and save lives, and this was widely considered to have won the war for the Allies. So it was hugely important, and tragically you know, Alan Turing suffered a very unfortunate I suppose end after horrible mistreatment by the UK government, but that's besides the point. These Enigma machines, though, they weren't computers because, as we've said about 5 times before, they weren't general purpose. They were designed to do one specific thing. If you want to learn more about this, if you happen to have not watched it, I imagine a lot of you have, the Imitation Game film. I know there's probably not a lot of time between now and the 24th of May to actually get this to get that film watched, especially to balance all your other subjects with study and whatever. But if you happen to really want to watch it, it's there. Vacuum tubes. Okay, these are weird looking yolks. These control the flow of electricity. Do you remember our semiconductors from earlier that could be used to control the flow of electricity? Well, these are the predecessors of these guys. So you can kind of see them. They're a bit unruly, especially in comparison to modern technology. But they were found in radios and TVs and, you know, computers of the time. And these, you know, by the standards of the day, they were small and they were low cost. But they managed to kickstart this modern electronic era of computing. So when we look at these electronic computers, we have a few. So we have the Colossus supercomputer at Bletchley Park with Alan Turing and his team. While it was electronic, it was not technically a computer because, you know, again, it was designed for code breaking, specific purpose, not general purpose. The ENIAC, or I'm just going to pronounce the letters. It's the first electronic programmable digital general purpose computer. This one ticks all the boxes that we've sort of laid out earlier. Okay, it couldn't store its programs in memory though. You had to manually, you know, unplug cables and control switches. You can kind of see all the different cables running in and out of it. You have Kay McNulty, an Irish woman who was a programmer. I believe there's the Computer Science building in DCU is actually named after her. And you notice the AC at the end stands for an automatic computer, because as we mentioned earlier, a computer was still a human. It was still a human job, but this was sort of the advent of machines being computers, if that makes sense. So they were now devices. They were no longer people. So the definition of a computer at this point in history has changed. It's interesting. So that was the first generation of computing. Okay, the vacuum tubes and the electronic computers. That's what we call the first generation of computing. We're going to go through the other 3 now. So we have the second generation of computing, the transistors. These are small electronic switches. So these guys replaced they replaced the vacuum tubes because they did the same thing, but as you can see, they're much, much smaller. They're tiny little yolks. So they were first developed at Bell Laboratories in the 1950s, and they had many use cases. They were used in the IBM 608, which is the first commercial fully transistorized computer, and they paved the way for various supercomputers as well, such as the Control Data Corporation 6600. That's what the CDC stands for. It's the first, I suppose, commercially viable supercomputer. About 3 million operations a second, and in today's money costs about 20 million euros. So, not your average machine. Then you have the third generation of computing. So this sort of came about in the 1960s. You have a number of electronic circuits all on one semiconductor or chip, as we commonly say. You have examples of computers built using integrated circuits. The ACG, or the Apollo Guidance Computer, which was used in the Apollo missions. The team was led by Margaret Hamilton, who helped design and program the software used by the Apollo Guidance Computer, and this made the likes of the moon landing possible, because that was one of the Apollo missions. So this is very important. You can see Margaret Hamilton. I've pictured her there. So the integrated circuits, they're bringing about this rapid increase in computing power. It's almost too fast. And then you have the likes of Seymour Cray, who started work on the aforementioned CDC 6600. He left and invented Cray Research, which developed the Cray 1 supercomputer, which sort of started this modern era of supercomputing. Then we move on to the fourth generation of computing, which has sort of carried into the present day. This is kind of where we are now. A microprocessor, also more widely known as a CPU, or central processing unit, takes in binary data, performs operations on it using instructions that it has stored in its memory, and then it outputs the results. We've all used a computer with a microprocessor before. You're probably watching this on a computer with a microprocessor. In fact, you are. The first one was developed in 1971, the Intel 4004. But nowadays you have microprocessors with billions of transistors on a single chip. If we go back, you can see that's one transistor, but you have billions crammed into tiny chips now, which is absolutely ridiculous. You wonder how it was even possible. So this managed to kickstart this PC revolution, the advent of personal computers, where people could afford to have a computer in their home for the first time. Computers were no longer something that were confined to like a whole room in a university. People could have these like in their offices, on their desk, to help them in their daily lives. So you have with the microprocessors comes personal computers. They arrive on the market in the sort of 70s, early 80s. You have manufacturers like Apple and Commodore and IBM. I've pictured here the Apple II computer, which was a popular choice in the late 70s, early 80s as a personal computer in the home. But of course, computers could only really be used by programmers up until this point. So this sort of created a need for user friendliness. Okay, so you have operating systems like Windows, which was created in the 80s and is still in use today, because it sort of allowed the everyday person who doesn't know how to code at all to use a machine, to use a computer. And then you have other devices such as keyboards and mice that allow people to easily interface and use a computer. So if we look to today, computers are everywhere. If your phone, it meets all the criteria for a computer, it is a computer. You have TVs now have smart TVs, so they'll have computers built into them. You have if you have a smartwatch, that'll have a processor in it, and it'll be programmable, so that'll be a computer. So you know, they're nowadays, you know, computers by comparison are actually quite affordable, and they greatly exceed anything that would have been made in the 1980s. And you know, supercomputers such as I've pictured the Summit computer from IBM at IBM here, they can perform quadrillions of calculations a second. So you can sort of see, I've put it in a single number. That's 1 quadrillion there, 1 followed by 15 zeros. That's a lot of zeros. That's a lot of operations. And the Summit has the Summit computer here has 9,216 CPUs. So supercomputers nowadays are very, very fast, like incomprehensibly fast. Then, if we relate this to Ireland, 14 of the top 500 supercomputers in the world are in Ireland. The fastest is like 302nd. The government does have a few on hand for research. The fastest of these is the K computer, after K McNulty, who we mentioned earlier, who was a programmer for the ENIAC computer. So this supercomputer is managed by the Irish Centre for High-End Computing, and it's installed at Waterford Institute of Technology, used for research. And we've had these supercomputers. We've had some supercomputers available to us as far back as the year 1994. So, you know, they've been in Ireland for a while, they've been available for a while, but, you know, I suppose in the future we might actually see more supercomputers in Ireland, especially as, you know, the tech industry in Ireland sort of expands. We have the likes of Intel here in manufacturing, so we could see more supercomputers in Ireland fairly soon. So the 4 generations of computers that we were talking about, we're just going to summarize these. The first generation, vacuum tubes. They were, you know, small at the time, but still by modern comparison very big. Then you move on to the transistors, which were much smaller, cheaper, better. You know, then you have the integrated circuits, which were used in the likes of the Apollo guidance computer. And then you have, for the 4th generation, you have the microprocessors, which sort of carries into today with, you know, because every computer nowadays uses a microprocessor. The 5th generation, if we just sort of look towards the future, we could have quantum computing, which, while we'll just briefly touch on this, you know, could be viable for a next generation of computing, but it's still going to take a lot of research, and for now microprocessors are holding out just fine. So thank you very much for taking the time to watch and listen to this. If I decide to do another one of these, the next one will be Computer Systems Chapter 6. That's the next chapter in the book. I started with Chapter 5 just with these because it's sort of, certainly in comparison to other chapters, it's short enough in the textbook, and it's just a bit of a nice one to have a trial run of. So I will probably make another one of these, or a couple more. I'll certainly be making the PowerPoints to send on. If you want a copy of this PowerPoint for yourself, I'm happy to send it on to you. Get in contact. Thank you very much for watching, and good luck with the leavings.